So good evening, everybody. Today again, we'll continue with the uh, topic that we left last time, that is defects. And more precisely, we left on what are one-dimensional or line defects. So all of us know by now that line defects are also called as dislocations, okay? And we studied about that there are two types of basic dislocations. One is called edge dislocation, the other is called screw dislocation. And rest of the other line deformations that happen in the crystal can be explained by combination of these two. Okay. So edge dislocation, I'll just repeat very briefly, is when you have a plane and that plane starts from one end of the crystal but it parts midways, then that particular line where that crystal plane finishes is your edge dislocation. In case of edge dislocation, your Burgers vector, or the vector that quantifies the magnitude and direction of your line dislocation, is perpendicular to the edge dislocation. This is very nicely explained in this book by V. Raghavan, which is Material Science and Engineering. If you want, you can refer to this one. Okay. In case of screw dislocation, what happens is the dislocation happen in such a way, we talked about it, that now the planes that across that dislocation, that those were actually parallel, have now become continuous. As you can see in the figure that is given on your right hand side. In case of screw dislocation, the Berger vector that quantifies the screw dislocation is parallel or anti-parallel to the dislocation line. Okay. Now, coming to the new thing today, how can dislocation move, right? Suppose we have some dislocation and we are able to see it by microscope and we want to remove it. So how can we remove the dislocation? They can be removed either by applying stress or by increasing temperature. And how can we do that? This cartoon on the right hand side will show you how. If you look at this structure, this is the plane that is parting midway, okay? This is your edge dislocation. Now suppose I put my hand on the top face of this crystal and I apply the pressure in this direction. What will happen is, if you look at this figure, this plane will combine with this plane. This atom will combine with this atom, and now this plane will become half. If you apply some more pressure, this will combine with this, and then this will become half. So this is how the dislocation line will move from left hand side to right hand side. So as is clearly visible, if you go from this figure to this figure, the plane which was half here is now half here in this point. As you move from this to this, now what has happened is this half plane has moved to this particular position, and eventually it will come out of this particular plane on the right hand side. Okay, and once it is there on the surface, then it is no more a dislocation, then it becomes the surface defect. Okay, so also the same phenomena can now happen by increasing temperature. And how would that happen? As the temperature increases, your atom vibrates with more and more amplitude, and when they vibrate, there is a chance that this B1 will combine with C4, and then finally this D1 will combine with C1, and by whatever phenomena I just explained few minutes back, this particular dislocation will come out of this plane and it will become a step on the surface. Okay, the half plane will be on the other side of the surface. So how can we remove dislocations? By applying stress, by increasing temperature. Okay, now can two types of defect interact with each other? Let's say, can I say that suppose in a particular crystal, both line defect and the point defects were occurring, would they talk to each other? Would there be some kind of interaction? Yes, this might happen if there is a decrease in total energy. that is the sum of the energy of the dislocation and energy of the point imperfection, then your crystal would absolutely love to have that kind of interaction. Just to explain you what do I mean by this, now you consider this particular figure, okay, or rather, let us consider this particular figure. Now, suppose, as I told you, above this point, the atoms are constricted, they are more closer. The average bond length is less than what it should be at the equilibrium value. And below this, the atoms are a little in the expanded phase. The R is greater than R equilibrium. So now if you have a point imperfection here, and what are your point imperfection? Vacancies and interstitial. Suppose I had a interstitial here. Now, if that interstitial was bigger, it will try to adopt this particular space because here your atoms are expanded. The space between them is more than what it generally is in the equilibrium position. So, and the net result would be that the system's energy, the free energy would decrease. Okay. And if it was a smaller ion, it would rather go into interstices on the above part. So this is what I meant when I say that dislocations can interact with the point imperfection if there is a decrease in total energy. Okay. Coming to 2D or interfacial defects. So as the name suggests, they are the defects which are across two-dimensional. Okay. So the region of the distortion is about few atomic distances. Again, I don't know whether I told you that in case of line imperfection, I must have, like your point imperfections such as vacancies, interstitial, Schottky, and Frenkel are thermodynamically driven and stable. Line dislocations are not thermodynamically driven. They are associated with high energy. They tend to increase the energy of the crystal system. And the same is true with your two-dimensional or interfacial defects. They are not thermodynamically stable, but they could be metastable or they could be unstable in the nature and they lead to increase in energy of the system. Let us talk about some of the common two-dimensional defects. First and foremost, the free surface of the crystal or the free surface of the crystallite if you're talking about the powder sample. That itself is a defect. How is that a defect? Why? Because when I break my crystal, let's say it is divided into two parts here. Now there are broken bonds either on breaking or on the surface itself. Suppose you've grown the crystal, and I'm talking of let's say CCP or HCP. Now, inside your crystal, all the atoms are 11 or 12 coordinated, but the atoms on the surface will be less than 12 coordinated. All the bond valencies are not satisfied. When they're not satisfied, your surface is associated with high energy. It is a defect area. It is a surface defect. Okay. So the very first defect that we learned about is that the free surface or the surface of the crystallite or crystal is in itself a two-dimensional defect. Grain boundary. All of us have heard about grain boundary. What is a grain boundary? It is if I'm talking about a polycrystalline material, most of the things that you see around you, whether it is sand or a piece of iron or anything, all of them are polycrystalline. Okay. So interface between two grains in a polycrystalline material is called a grain boundary. And how you can visualize it very well in this particular figure on the left hand side, where these small things are the grains and these blue lines are nothing but your grain boundary. And it is again shown here, these two are grain A and grain B, and this is your grain boundary. So what actually is a grain boundary? Is it a line? No. Is it something that we've drawn? No. They are actually the cluster of atoms which have not been able to adopt the crystal structure which was predominant in the grain. And why does that happen and how does that happen? Suppose you're growing a crystal from the melt, or there is a solid state reaction happening. To make the things easy, let's talk about the crystal being grown from melt. So what happens is, the nuclei are formed at various places, small nuclei as the crystallization happen. And as more and more crystallization happen, or let's say two reactants A and B are reacting and they're forming a product AB. So first the nucleation occurs, right? And then these nuclei attract A atom, B atom towards themselves and they start increasing in size. And since nucleation will happen at many places, so each nucleus will do this process. It will keep on attracting A and B atom and they would keep on falling in a particular three-dimensional arrangement which is specific to my AB. Now what will happen? Suppose these crystals have grown this much, a point will come when there would be A and B atom which would be attracted in an equal and opposite way by both grain B and grain A. Okay, and they are feeling equal and opposite force, so they won't be able to move. So what will happen is they will not actually crystallize in the structure which is supposed to be for the product AB. So it will either be an amorphous region where there is no periodicity at all, or it could be a geometry or symmetry which is not similar to what is prevalent for your grain or what is supposed to be for your product AB. And this region ultimately is called the grain boundary. So basically, what happens is, again, this shows the grain boundary, and this is a real scanning electron microscope picture of a stainless steel sample where you can see different grains and their boundaries are, of course, the grain boundary. Okay. Now, these grain boundaries, as we saw, that the grains across the grain boundary, here the crystal structure is similar to what the crystal structure is here, but they are tilted or twisted by certain angle. Okay, if the axis of rotation, so now in terms of what is the how can I describe this grain boundary? If my grain boundary can be represented in terms of two or more edge dislocation, what I want to say here is, suppose these two grains are oriented with respect to each other, and as I told you, I can represent my edge dislocation by this. I can represent it by this, and then it was slightly by this, and then it was slightly by this, and I am able to reproduce this orientation in this particular crystallite. So what I want to say is that if the misorientation that has happened in two grains, it can be represented by two or more edge dislocation, then your grain boundary is given a specific name and that is called tilt boundary. Okay, that is they are tilted with respect to each other. But if that misorientation can be represented in terms of two or more screw dislocation, then that is called a twist boundary. So as we know, as we talked about why the screw dislocation got its name, because it's kind of similar to the movement of the screwdriver. Okay, so if the misorientation can be represented by twisting in terms of two or more screw dislocation, it is called the twist boundary. Okay, how can I reduce the grain boundary? Many a times, if I'm working on ionic conductors, now grain boundaries have got much higher resistance than your grains. I would not want my material to be highly resistive. I would want to decrease the grain boundary. How can I do that? The grain boundaries can be annealed. Annealed means leveling out. Grain boundaries can be annealed by increasing the temperature. So when you increase the temperature, the smaller grains they coalesce. Coalesce means they come together and they form a bigger grain. And when the smaller grains coalesce to form the bigger grain, obviously there is decrease in number of grains, there is decrease in number of grain boundaries. Okay. And also there is something called high and low angle boundary. This is nothing but the terms used by metallurgists and material scientists to actually define extent of misorientation between the two grains. I have a grain A, I have a grain B. If their orientation is more than 10 to 11 degree, they are called low angle grain boundary. If the, sorry, less than 10 to 11 degree. If it is more than 10 to 11 degree, they are called high angle grain boundary. These names are very, very self-explanatory, so you don't really need to remember it. All right. Interface boundary. If I know what a grain boundary is, my grain boundary separates two grains, but the composition of those grains are similar. Okay, if I'm talking of A, then grain A, if I'm talking of a grain boundary, then grain A and grain B will have same composition. But if the composition of grain A and B are different, in that case, my interface or my grain boundary would be called interface boundary. Okay, very simple. Just few nomenclatures that you have to remember. Apply a little logic, and that's not going to be difficult at all. So this is just one TM figure that I thought I should show you. Okay, if you can see this high resolution TM, you can see that in this particular figure, these atoms are arranged in a particular. Uh, mm, okay, so arrangement of these is similar to arrangement of this side is similar to arrangement of this side, just that they're tilted with respect to each other a little bit. They are not misoriented. And as you can see, this is a low angle grain boundary. They are actually misoriented by a very small angle. So grain boundaries, of course, when you look at your crystals or particles through electron microscopy, obviously you will not be able to see any lines which we drew on the previous slide. What you would see is something like this, and then you say that this is grain boundary. Similarly, here, okay, so this is how we observe grain boundary. If you have TN, by SEM we are able to observe this kind of figures, and there you can of course observe the grain boundaries as lines. Okay, all right. Twin boundary. Now that's an interesting thing. As the name suggests, twin boundary is a pair of boundaries where across which your crystal structure is a mirror image of each other. And they always occur in pair so that the change brought about one is undone by other. Okay, so that is your normal crystal structure. This is one twin boundary. So if you can imagine this, actually this crystal structure on the right hand side is the mirror image of this, but then the other part of the twin boundary always occur in pairs. That is why they are called twin boundaries, right? It undoes the change which was brought up. This particular line undoes the change, undoes the change brought about by this line, and now the crystal structure kind of continues. Okay, so twin boundary by definition is a 2D defect across which the structure is the mirror image. They occur in pairs so that the change brought about by one is undone by other. A twin boundary, which is a planar defect, is shown where the displacement of the atom by stress reorients the volume of the crystal, and it is bounded by a twin boundary. So these are actually observable, not just by electron microscope, but you can also observe this twinned region. This region would be called the twinned region. They are observable even by optical microscope. Okay. Stacking faults. Another very interesting 2D effect. Again, as the name suggests, it is because of the faulty stacking of the closed pack layer. How? For example, what is your CCP packing? It is ABC, 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 right? On your left hand side is a CCP packing, which is a perfect crystal. ABC, ABC, ABC. Now, somehow, if it happens that the orientation of layer in this particular C is changed in such a way that it is kind of a layer, we can do that by placing them in the different end, by placing it exactly over the third layer exactly over this layer, then what will I have is ABC, AB, AB, and then again it will continue. So what has happened actually is this was a CCP and you have introduced this small HCP kind of a region in CCP. And why has that happened? Because of the fault in how the layers are stacked. And because it is a fault in how the layers are stacked, this is called stacking fault. They can happen during crystal growth and they can also evolve from other defects. Okay? Bulk or volume defects. Now, bulk and volume defects are actually more voluminous, as the name suggests. You can observe them in a better way. And what are bulk and volume defects? They are pores in your crystal and they are not related to your crystal structure. They are not the vacancy that is there in the crystal structure. It is rather a pore or the vacancy, not the vacancy, but rather an empty space that is there in the morphology of your material, not in the crystal structure of your material. Okay, then cracks, foreign particle which have come into your material, all these are called bulk or volume defect, and they are introduced usually during the processing and fabrication operation. Again, they are stress raisers. All barring your Schottky, Frenkel vacancy and interstitial defect, 1D, 2D, 3D, all these defects, they raise the stress, they raise the energy of the material. They could be deleterious, but sometimes they're deliberately introduced for getting some particular property. Okay. So, and sometimes, they are added, as I said, why? Sometimes foreign particles are added to strengthen the solid. Why? We just make them as dispersion. Now, these particles that are dispersed in your original host material, they do not let the dislocations, as we saw that if I apply the stress or even if the temperature is raised, the dislocations will move. Now, I don't want my material to be, in whatever situation I've kept it in my device, it should be like that. So these particles, they add hindrance to the movement of dislocation, and that is why they increase the hardening. Just one example of how these are sometimes deliberately introduced. Okay. So with this, we kind of studied about general kind of defects that happen in material science. So how do you study the defects? Okay. Suppose I want you to understand the defects are, what is the concentration of defect or whether the defect is present at all, qualitative and quantitative determination. Point defects can be studied by conductivity study. This we'll study about in a little more detail. UV visible. Why UV visible? Because if this is suppose your band gap, conduction band and valence band of the perfect crystal, if some defects are created, they create some kind of a trap here. Okay, so they form lower energy region and they might fall in the your visible or the UV region, and then by UV visible spectroscopy, you can know, understand, study those defects. Dielectric study. In a very, very layman's language, what is a dielectric constant? How does a dielectric constant happen? It is because of movement of your positive and negative center of the crystal with respect to each other. Okay, that creates the dielectric constant. But if you have a lot of point defects, then this will affect your positive and number of positive and negative ion, and it will manifest in your dielectric constant. Dilatometric, what is dilatometry? Dilatometry is nothing but what you are trying to do the thermal expansion. You are dilating. You are studying the thermal expansion of the material. So by thermal expansion also we can study the defect. Suppose you have vacancies and you are heating it, but your bonds are also expanding. But if there are vacancies, they will act as a buffer. They will try to absorb that expansion. Okay, and that will have effect in your thermal expansion coefficient. So dilatometric, dielectric, UV visible, conductivity is not the exhaustive list, but some of the studies that you can use to understand your defects. Okay. Nowadays, of course, we have so many sophisticated technique. There's something called positron annihilation spectroscopy. So that just remember the name. Okay. Positron annihilation spectroscopy, also abbreviated as PAS. This is also a very, very well-known technique to nowadays. Of course, it is not available everywhere, but a nice technique to study point effects. Okay, 1D and 2D, good thing about them is though you can observe them, they are not just a point. So depending on how big they are, if they're very small, you can use electron microscopy, or if they're kind of like, twin boundary, we talked of twin region or the 3D defects, I mean, which you can observe, that you can observe even by optical microscopy, but they are to be observed. Okay, so it's like electron and optical microscopy sometime. Okay, let's not talk about that to confuse you further. Color center, because they're color centers, so by virtue of that itself you would know that you can study them by UV visible spectroscopy. Sometime you can also study them by X-ray spectroscopy, where you need to excite them by X-rays. So these are general technique. We'll talk about this particular thing, conductivity study, how you can do, because that's a nice thing to understand the concepts. Okay, let's just talk about NaCl. Okay, first and foremost, I'm sure I've discussed about it when we were talking about structure property relationship. How can a material conduct, right? You have to give it a pathways. Now, NaCl has got atoms, and it's a hard solid. Like Na also is a hard ion, Cl is a hard anion. So unless you create some defect, NaCl will not conduct. It is a poor ionic conductor, and I am not talking about NaCl dissolved in solution. I'm talking about NaCl solid at room temperature. Okay, so whatever little conduction happens, it's a poor conductor, but that is due to migration of your cation vacancy. There is a vacancy. Ultimately, what is conduction? It is a movement of charge, right? This Na will go here, a vacancy is created here. This Na would go here, a vacancy would be created here. Now, either an Na from here or this Na would go there. What is happening is a movement of charge, that is conduction. And that in case of NaCl happens by migration of cation vacancies. Now, how can you get cation vacancies? Okay, we studied that NaCl can have Schottky defect that will create cation vacancies, right? And that are bound to be there by due to thermodynamic reason. You can't control them. You can't ask them to not happen. Okay, and the defects that are present in the material due to thermodynamic reason are called intrinsic defect. But if you create the defect deliberately, then you're doing it due to some external factor. They are called extrinsic defects. We are clear on that? Now, as I said, NaCl conducts due to cation vacancies. Now, the cation vacancies can be present either due to Schottky defect, which will anyway be present, and that will also depend upon temperature, or you can deliberately put it. How can you deliberately put it? Okay. Suppose I substitute some CaCl2 in it, right? I'm replacing Na plus by Ca2 plus. And because I am increasing the charge, what happens is some of the positive charge will have to go. And how can it go? Some sodium ion vacancies would be created, right? Now, what I do is I can have two types. I can create sodium ion vacancies by two methods. One is, I mean, I cannot create. I can create only by one method, by doping an eluvalent ion. Eluvalent is the charge is different from the host ion, or it will itself be generated by Schottky defect. The ones that you are generating by Schottky defect depends on temperature. You remember the Arrhenius equation? More is the temperature, more will be this. But the one that I'm creating by doping in alluvalent ion is in my hand. That will depend upon how much calcium will I dope. I will know how much vacancies I can create. And now this is fixed, because if you increase the temperature, the vacancy created due to this substitution is not going to change. All right. So, yeah. So what we do is Let's say I substitute 1%, 1 mole percent of calcium ion in place of sodium ion. I know that 1% of vacancies are created. Now we determine the conductivity. There are conductivity meters, AC impedance analyzers by which you can measure conductivity. So this is your Arrhenius equation. If I make it this way, I can say it is log natural sigma is log natural sigma naught, which is a constant, minus EA upon KT. That means if I plot a graph between log natural sigma by 1 by T, I should get a straight line with a negative slope. Now since this is 1 by T, so this is your lower temperature and the temperature is increased in this direction. At lower temperature, your Schottky effects are lesser, right? Because they increase with increase in temperature. But whatever defects you had created by substituting calcium for sodium, they are there. Okay, so the conductivity would increase as you increase temperature. And here the slope of this is, because slope has to be the activation energy. Slope is, let's say, I say E1, or I can say EM because I've shown that in the figure. Now, beyond a certain temperature, the Schottky effects would be created because it is exponential dependence. Okay, the Schottky effects would be created in much higher amount, and then this slope of this thing would be increased. And here, your slope is not okay. This activation energy. What was this activation energy? This activation energy was the defects are already there. You do not require energy to create defect. They were created only because you substituted calcium. But this is energy for mobility, to the energy hindrance that your ions are facing to move. Okay, so this is the activation energy of mobility. But here, when you are in this region, now this activation energy is a sum of EM plus EF by 2. Okay, and what is EF? EM is the energy. Now, whether your defect was created by doping of calcium ion or it was created by Schottky defect, the energy that you would need to make it move is similar. So that is EM, and that is same as what it was here. This EF is the energy that you require to create a Schottky defect. And this equation we have studied when we were talking about Schottky effect, which is this. All right. So to keep the thing simple, if I do not know all these things, what I'll do is I'll determine conductivity. I will plot log natural sigma by 1 by T, temperature increasing in this direction. As I increase the temperature, I will get something like this. Of course, it won't be very sharp. I'll measure the slope here. This will give me my energy required to make the ions mobile. If I measure the slope here, this will give me the sum of the activation energy required to make my ion mobile and also to create the Schottky effect. From this slope, I can measure EM. I know this slope is a sum of these two, so I can know what EF is. And once I know EF, by this particular Arrhenius equation that we studied during Schottky effect, which is N is N naught exponential minus EA upon 2RT. You remember 2 came because of this thing, because Schottky effect and Frenkel effect occur in pairs. That is why this is EF by 2 here. All right. So once we know EA or EF, as is mentioned here, I can calculate N. So I can know how many defects are created in my material, and then I can do whatever I want to utilize this data. Okay. So this is how we study the concentration of thermodynamically generated effect. And every technique has got, this is for ionic conductivity. Every technique will give you some correlation with the defects that you want to study in that particular region. Okay. So basically, in this topic of defects, what do we study? We studied about defects and why do they occur? 0D, 1D, 2D, volume, classification of defect based on dimensionality, based on whether they are created extrinsically, intrinsically, based on whether they are thermodynamic origin and not, and so on. How can we determine the concentration of thermodynamically generated defect and how to study these defects? Okay, so with this, we kind of wind up the topic on defects, but we will now, okay, one more thing. Your Schottky defect and your Frenkel defect, they do not disturb your stoichiometry. That is, if I started with NaCl, because my Schottky defect will take away one NaCl, ultimately the ratio of stoichiometry is ratio that you started with. All right. My ratio of NaCl is not going to change. Similarly, in Frankel, I'm simply removing one Ag from a particular place and keeping it in the interstices. Even this is not changing your stoichiometry, ratio of Ag to Cl. So the defects that do not disturb your stoichiometry are called stoichiometric defect. So in next few minutes, we will study which is called something which is called solid solutions, and that is also related to creation of non-stoichiometric defect. Okay, so we'll take a break for 5 minutes and then we'll come back to this. Thank you. All right, so we'll now study about solid solutions, which are also an example of extrinsic defect because you're deliberately trying to introduce guest into host solution, host material, or the non-stoichiometric defect. Okay. What are solid solutions? All of us have read about and studied about liquid solution. When I mix two more than one liquids, we get liquid solution. Same with solid solution. It's a solid that has got two, three components, right? And now my biggest doubt is how is a solid solution differing from a compound? Because a compound also has many a times more than one cation. It has can have two ion, two, three cation, four cation. So how is my solid solution different from a compound? Okay. So what is it is both of them are crystalline phases, okay, whether it is solid solution or it's a compound. But your crystalline phase that has got variable composition, that is solid solution. When I call something as a compound, then it does not have variable composition. All right. So what I want to say is, if I can mix my A and B in a large amount, still maintaining the same structure. Let's say AB10, then which is A1B10, A2B8, A2B9, A3B7, and so on and so forth. And still my crystal structure is same. I call this as a solid solution. But when I'm talking about compound, my compound does not have a lot of tolerance for maintaining the same crystal structure, even after varying the composition. Okay. So in nutshell, solid solution is a crystalline phase having variable composition. Okay. Now, fine. So this is what I just described. Okay. For example, these are the example of two solid solution. If I take aluminium oxide and chromium oxide, it is observed that in whatever quantity I mix them, they form solid solution in entire range. Similarly, in case of ceria and thoria, whatever quantity I mix them, they mix across this entire range without giving any heterogeneous or second phase. Okay. So these are the example of solid solution. And you have to remember that the structure, if I'm mixing aluminium chromium oxide, or in general, if I'm mixing two components A and B, then the structure of AB solid solution could be either similar to one of the end members A or B, or it could be different. So it is not necessary that AB would have structure similar to A or B or both of them. It could be entirely different also, but as long as it is a solid solution, it will retain its own crystal structure. Why do I study solid solution? I mean, why we already have so much work at hand? Why do I just pick up this topic and do that? This is important. We have talked about in structure property relationship. Modifying the composition modifies the structure, or otherwise also if it retains the structure, modifying the composition is a very, very unique and effective way to control structure and properties. Okay, so modifying the composition means you are substituting one or two of the ions of your given compound by a guest cation. Okay, and that also you have chosen very wisely based upon some criteria. So you're modifying the composition and you're controlling the structure and you're controlling the property. And this is what materials chemistry is all about. Also, it provides you an avenue to obtain better materials. Not it just does not let you control it, but you can alter the properties in whatever way you want, giving you access to better materials for a particular application. For example, I have ZrO2. ZrO2 is monoclinic at room temperature. If I substitute alkaline earth, what are alkaline earths? Barium, calcium, magnesium, strontium. or rare earth. What are rare earths? Lanthanum, cerium, the entire F block series, into ZrO2. It creates vacancies and it gives you cubic zirconia. Cubic zirconia is technologically a very, very important compound as a high temperature ionic conductor, solid, and that has application for solid oxide fuel cells. Dope ceria, again, we can dope different ions into ceria, create vacancies, which makes it a very good ionic conductor. Barium titanate, we talked about it twice or thrice. We can play with the structure by substituting barium by some other ion, or by substituting titanium by some other ion, or by replacing both of them to some extent. And by that, we can actually tune its ferroelectric transition temperature. Okay, that is why solid solution are important, because they give you keys to play the video game to get better materials. Now there are different types of solid solution, simple and complex. Everything in the life is like that. It could be either simple or complex. Let's talk about the simple solid solution. There are of two types. Substitutional solid solution, wherein you're substituting your host ion by the guest cation and doing nothing. Or interstitial, wherein you're absolutely not taking anything from your host, but you're taking the guest ion and putting it into interstices. Hence the names substitutional solid solution and interstitial solid solution. So what are substitution solid solution? When your guest atom or ion replaces the host atom or ion. This is one such example. Suppose you take 80% of AO2 and 20% of BO2. Effectively, it means that you took AO2 and in your material, you put 20% of B, because both of them are O2. That is going to be same. And you get something like this, if at all. This is your substitutional solid solution, because it has done nothing else to your material. No vacancy, nothing. A and B were similar charge and you got this solid solution. I call AO2 as the host, I call B4 as a guest. B4 plus directly replaces A in substitution solid solution. Now, what are there are certain guidelines, again, as I've always maintained, that you don't really need to learn, because they're very, very logical and very, very kind of a general understanding, common sense thing. But they've been given the name because, when they were being put forth that time, they had to put some guidelines. And the guidelines that govern the solid solution formation are called Hume-Rothery rules. Now, what are this? They say that your end members, and what are your end members? Your host and the guest. So basically, I cannot have an ionic radii. I'm talking of only A and B here. End members should have similar sizes. Okay. More similarity in their size, higher will be the solubility. Very, very common sense thing. They should also have similar charge. They have similar size, they have similar charge. Basically, they're simply replacing each other and they're not disturbing the structure. If they do not have similar charge, then the solubility decreases and it forms the complex solid solution. And we'll come to it later on in the lecture. And the end member should be isostructural. Okay, that is, they should have similar structure. This is not always necessary, but if they do, the solubility increases. Again, a very, very general sense. So what Hume-Rothery rule says, that you want to have as much as solid solution as you want as possible, maximize it, look for the ions that have similar size, look for the ions that have similar charges, and if your end members can also have similar structure, that'll be good for you. Okay, so again, the rules are simply guidelines. The most important thing here to understand is whether a solid solution will form or not form. It cannot be predicted. It only can be done experimentally. Okay. But as all of us, especially the scientists, they work on intuition. Okay. So if you have already been working on similar kind of material, you can have a very good intuition about whether these two things will mix up in the solid state, whether they will retain the same structure or something else would happen. But that would come only by experience. Ab initio, Formation of solid solution cannot be predicted. It has to be done experimentally. We talked about, as I said, the simple solutions are of two types, substitutional, second is interstitial. Interstitial solid solutions are those where you are inserting the guest atom in the interstitial site of the parent structure or the host structure. A very common example is all of those who are chemists have been studying about palladium hydrogen catalyst right from the beginning, used in many of the organic reactions and is a very good catalyst also for other kind of things. So what happens is here your hydrogen breaks up into hydrogen atoms and those hydrogen atom goes and sits into the interstitial sites of face centered palladium. A very common example that you come across in your daily life many a times a day are steel, stainless steel. What is it? It is nothing but carbon sitting in the interstitial sites of FCC iron. Okay. Good. So these are about the two simple solid solution. Another interesting thing that I would want to talk about is substitutional solid solution. We talked about, let's say, alumina chromia we talked about, or cerium oxide, thorium oxide. Okay. So everywhere I saw whatever example I took, I was replacing cation by a different cation. Can we have the solid substitutional solid solution wherein anions replace each other? It happens, but it is rare. Why is it rare? Because there are not many anions which have got similar sizes and bonding requirement. Okay. And that is the reason anionic substitution solid solution, let's say, what I want to say here is AX and BY. So whether Y can replace X or X can replace Y, it happens, but it is much less common than the cations replacing each other. So that was about complex, simple solid solution. Okay. No problem with charge. You only had to take care that the size was similar. Okay. Now what happens if your charges on host and guest ions are different? Okay. Here, what I want to say is, suppose I have AX as the host and I am replacing BN plus as a guest. What can happen? Your BN plus can be greater than A. That means charge on the guest is greater than the charge on the host. Or it could be lesser than A. Charge on the host is greater than charge on guest. In case of complex solid solution, you only have to remember one thing, that it will try to, unless you give it an option. Okay. And when I say you give it an option, I'll give you an example. It will try to maintain electroneutrality on its own. Nothing in this universe wants to remain charged. Okay. In the first case, when your cation, substituent cation, that is your guest, had higher charge, what is it doing? It is actually increasing the positive charge in your material. And for that, what you can do is you can decrease the positive charge. There are two ways. How? You remove some of the cation, and that is given the technical term of cation deficient solid solution. Or you also increase the amount of anion. Positive charge is increased, na? Increase the amount of anion also. Negative charge also. And negative charge are the anions. The technical term given to it is anion excess solid solution. Coming to scenario 2, where your guest ion has lower charge than your host ion. In that case, the positive charge has decreased. Okay. Cation deficient. Now your guest ion, the charge is lesser, positive charge has decreased. So you will have, you will decrease, you will also have to decrease the negative charge. And in that case, you will form anion deficient solid solution. Or you increase the positive charge, no, put more more cations, and that will give you cation excess solid solution. So we'll talk about one or two examples for all of this, and let's see how it happens. Okay. So example of your guest cation has got higher charge. We'll take the very simple example that we talked about earlier also. You're substituting calcium in NaCl. Okay. So every calcium that enters in place of NaCl is actually 1 of Na plus is getting replaced by 2 of calcium. That is, every calcium is getting 1 extra positive charge, right? That means I need to introduce 1 extra negative charge, or I can just replace I can just remove 1 positive charge. Okay. So how can we write it as, if I want to write cation deficient, that means, let us put it this way: NaCl, calcium, and vacancy. I'm talking of cation deficient. For every calcium that enters, okay, let's say for every X calcium that enters, sodium, now let's say sodium is 1, you are now creating cation deficient. Okay, that means it is I've removed 1 sodium, put 1 calcium, but I want to create a cation deficient solid solution. That means 1 sodium also has to go, because now I have to balance the charges. So for X calcium, X vacancies would be created, and how many sodiums have become less? 1 minus 2X. X, because X sodium were replaced by calcium and X vacancies were created. So 2X sodium have gone from the lattice. So this is the notation for your cation deficient solid solution. For anion excess, so that if I'm talking of anion excess, I will absolutely not disturb my cation side. X calcium come in, 1 minus X sodium goes out, but now I have to increase the negative charge. How much? Every calcium brings in 1 extra positive charge. So it is 1 plus X. That is the formula for anion excess solid solution. Why am I writing it for both? A, for your understanding. B, as I told you, we cannot predict what will be the mechanism of solid solution formation. Though by experiments now we know that putting calcium into sodium will create cation deficient solid solution. Okay. Now let's take a exercise. How can you write the formula for solid solution that can be obtained by substituting Nb2O5 in Fe2O3? Okay. So why basically I'm telling you all this, because those of you who would venture into materials chemistry would need to do these calculations if you want to do synthesis. Okay. So it's a good idea to good practice to have an idea of kind of solid solution you can expect. All right. And then one advice that I always give is, and it is not given in any of the textbook, is it is very difficult. See, when till we were talking about NaCl and CaCl2, no, the situation was simpler. Here I'm talking of a 5 plus anion. Here niobium is 5 plus, and this is Fe3 plus. Then even though it's not difficult at all, but it doesn't come that simple as 1 plus and 2 plus. So I always suggested that whenever you are asked to do such kind of questions or calculation, write it in terms of single of your cation. For example, you can write Nb2O5 as NbO5 by 2 or NbO 2.5. All right. And you can write your Fe2O3 as FeO 1.5. If you do this, the chances of mistakes would be very, very less. Okay. Now suppose, okay, now what I am doing is I am substituting Nb5 plus in place of Fe3 plus. I am increasing the positive charge. That means I can either get a cation deficient solid solution or an anion excess solid solution. How can I write anion excess solid solution? That should be an exercise for you, but okay, let's do this. Okay, let me give you one example so that you are able to solve this. Suppose I'm talking of anion excess solid solution. In that case, I am not touching my cationic lattice at all. Okay, that means my X niobium comes in, so iron remaining is 1 minus X. but I have to play with my anionic sublattice. So what was it? It was 3, right? Now I have to add some anion. And how many anion would I add? Okay. So that you can understand by each iron had a, uh, uh, let's say, okay, let me just make it simpler first. Let me simply write Fe, Nb, and it was FeO 1.5. Okay. Now I have to balance the charge. If 3 niobium goes in, then 5 iron 3 plus have to come out. How? 5 3 the 15, 3 5 the 15. Charge balance. Okay. So if I have that, and then I also have to understand each niobium is associated with 2.5 oxygen and each iron is associated with 1.5 oxygen. Suppose X niobium goes in, right? Every niobium is taking an extra of 2.5 minus 1.5, one extra oxygen. Okay, so if it is NbX, this is 1 minus X, then oxygen would be 1.5 plus number of niobium into 1. So that is X. Okay. Or I can also write it as Fe 1 minus X NbX O 3 by 2 plus X. Multiply everything by 2. You will get Fe1 minus X NbX 2O 3 plus 2X. All right. Take a minute to look at the screen. And if you don't understand, you type in the chat box after the class. I'll try to tackle that. Now let's learn to write how to write a cation deficient formula. Always remember this. 3 Nb go in, 5 iron come out. Okay. Now we have to write cation deficient. Very simple. Fe Nb, and we're talking of deficient, so we have to put vacancy. We're talking of cation, we have do not change the anionic side. For every niobium that goes in, for every 3 niobium that go in, 5 this come out. Okay. For every 3x, right, 5 iron have to come out. So iron will be reduced by 5x. Now only 3 of those 5 iron sites are occupied by niobium. 2 are vacant. So 2x. And that is the formula for your cation deficient solid solution. Okay. So with this concept, now you can write whatever solid solution formula you want, whatever valency goes into replaces whatever valency. Okay. Now this is the example that you would do by yourself. This is easier than the previous one actually. Suppose I have MgO and now you're substituting Al3 plus in it. The only thing that you have to remember is for electroneutrality, if 2 aluminium go in, 3 Mg2 plus have to come out. 2 3 the 6, 3 2 the 6. If you remember that, you will be able to write the nominal formula for the cation deficient as well as anion excess. All right. Now the second thing, if the charge on the B is less than A, till now we were talking about here the charge of the guest that is incoming ion is more. If it is less, for example, you are substituting calcium in ZrO2. Your Zr is 4 plus and calcium is 2 plus. So every calcium that enters, it reduces the positive charge. That means you have to reduce the negative charge, make it anion deficient, or increase the positive charge, make it cation excess, right? It is very simple to write that. If you want to write anion deficient, Zr calcium oxygen. Every Zr has got two oxygen with it. Calcium will have one oxygen, CaO, right? So it is simple. For every calcium that goes into Zr, X calcium, you replace it by X oxygen. Simple. One calcium goes in because it is CaO and that was ZrO2. One calcium goes in, one oxygen becomes less. X calcium goes in, X oxygen becomes less. Simple. If you want to write cation excess, I'm not changing. My anionic site remains 2. Okay. So for every Zr is 4 plus, calcium is 2 plus. For every Zr 4 plus that you are removing, you have to put 2 calcium. For every X Zr that you are removing, you have to put 2x calcium. It is as simple as that. This is basically this particular class, anion deficient zirconia, as I told you in the first slide, is technologically very important class of compound. They are superior oxide conductor, and by virtue of this particular property, they've got many applications, and SOFC, solid oxide fuel cells, is just one of them. Okay. Talking of double substitution, till now we were either replacing cation, we did not talk about anion at all. You can have double substitution also, wherein both the cation and the anionic site you can put something, maintaining the charge equal. How do we do that? Suppose I start with NaCl, I replace Na by Ag, Cl by Br, sum of it, and I get this solid solution. And why is this possible? Because chlorine and bromine, they've got kind of similar size, kind of similar bonding requirement. So it is possible for them to replace each other. Actually, we get only anionic solid solution of these form. Okay, here anyway we are talking of double substitution. Now this is also an example of double substitution. Si3N4 silicon nitride is a very high temperature material, and it can be improved in its property if we add alumina to it. If you look at it carefully, all of you know silicon is 4 plus. I'm replacing some of the silicon by aluminum, which is 3 plus. I'm reducing positive charge. But concomitantly, I'm also replacing nitrogen, which is 3 minus, by oxygen, which is 2 minus. So I'm actually replacing by the cation, which is lesser charge, replacing by the anion, which is also lesser charge. So the electroneutrality is taken care of, and these kind of material, silicon, aluminium, oxygen, nitrogen, silicon, aluminium, oxygen, nitrogen, are also given a pseudonym silons. Silons are the refractory material. What are refractory material? The material that have got very high melting point, and you can use them for high temperature applications. All right. So how can we study solid solution? We need to study, right? We just took A, B, mixed them, ground them, put it in furnace, we got something. Whether it is a solid solution or not, how would I know? X-ray diffraction, every materials chemist first friend. Okay. So first of all, how can X-ray diffraction, what will X-ray diffraction tell you? You record the X-ray of your material A, you record the X-ray of your material B. You mix them, grind them, make the pellet, put it in furnace, or in nutshell, carry out the reaction by whatever means you want. I told you about solid state reaction. Take it out, grind it, record the XRD again. Okay. So, if the A and B have completely mixed, you will get only one phase. If they have not mixed, you will get the peaks of A, the peaks of B, and the mixed phase, right? So X-ray diffraction, first of all, will qualitatively tell you whether the solid solution is formed or not. If at all it is formed, you can also determine all its cell parameter A, B, C, alpha, beta, gamma of the solid solution, because it is also, after all, a crystalline phase, right? That can be done from XRD. So XRD you can do qualitative, quantitative analysis of your solid solution. By density measurement, solid solution formation will affect the density. Why? For example, very logical thing, if you're getting vacancies, cation vacancies and ion vacancies, it will lead to the decrease in density from the density that you have calculated theoretically, which you think it should be. If interstitials are there, it will increase their density. Okay. So density measurement will tell us, will give an idea about what is the mechanism of solid solution formation, which I've been repeating in last few slides, that you cannot predict, you actually have to determine it experimentally. So density measurement is one such technique. Changes in other properties, for example, thermal analysis. If you have a solid solution formation, it is a crystalline phase. I was mixing A and B, I mixed them, I got a different crystalline phase. The melting point of AB will be different from A and B, right? So it affects the melting point. A very common example is that in iron, if you put even 0.2% of carbon, which is your steel, it reduces the melting point from 900 directly to 723. So these are also good indications to that there has been a formation of solid. If that carbon was not sitting inside the iron, if it was sitting somewhere else, it would not have affected the melting point of iron. That means it has done something to its structure. It has formed a solid solution. Now, I'll just demonstrate this. There's something called Vegard's law, which you should know. So what Vegard's law states that if you are mixing A and B, in different proportions, A90, B10, A80, B20, and so forth and so on, then the lattice parameter of the solid solution that you would determine by XRD, it will be the linear function of composition. What it wants to say is that if you have A1 minus X, B, X, and you're plotting A, which is cell parameter, let's say it's a cubic solid solution, with composition X, and B could be 10 to 100, then this will be the linear function of your composition. The cell parameter would be the linear function of your composition. But Vegard's law is a very, very ideal thing, and ideal things never work in the universe, right? All of us know that. Why does it fail? It fails. It is actually obeyed in many cases, but in many cases it fails too. The reason is, what is it assuming? It is talking about cell parameter. Cell parameter ultimately depends upon, suppose I'm mixing B in A, it will ultimately depend upon what is the relative sizes of A and B, right? There A is a bigger ball, B is a smaller ball, then always whenever I'm replacing A by B, the lattice parameter would shrink. If B is bigger, it will expand. So what is it assuming? It is assuming that the lattice parameter, host and guest atom are the hard spheres, they are the hard balls. And lattice parameter would depend only and only on their relative ionic or atomic radius. But it doesn't happen, right? There are many more interactions happening. If I forget about all those, in general also, if the interaction between AA and BB is greater than what it is between AB, they will not like it. And the lattice parameter will be more than what you are expecting. That is, you will get a positive deviation. If your AB interaction are much stronger than what was between the reactant atom, they will like it, the lattice would be compressed, compacted, and you will observe a negative deviation. All right. Just a simple example of, because all of you, whatever I taught, you're not going to see that. You're ultimately going to see the X-ray pattern. So I will give you one example of two systems that I myself did, Syria and YSZ. YSZ is nothing, whatever I told you few slides back, stabilized zirconia, anion deficient zirconia. By in ZR4 plus, I have replaced some of the ZR4 plus by 3 plus. So this is YSZ, yttria stabilized zirconia. So I mix YSZ with cerium oxide and I mix YSZ with thorium oxide. All these compounds have got strategic some importance, okay? And this crystal structure is fluoride type. Thoria is fluoride type, YSZ is fluoride type, ceria is fluoride type. And I tried to mix them in various ratios, but I'm showing only 3 patterns here. This is pure YSZ, the X-ray pattern of pure YSZ. This is the X-ray pattern of pure thoria. They look similar, they are only shifted Why? Because size of thorium is bigger than yttrium and zirconium. All right. But when I mix these two in 50-50 ratio, I saw that I get the set of peaks. One set of peaks marked with star belongs to YS set. One set of peaks belongs to thoria. That means thoria and YS set do not mix with each other. The solid solution formation has not happened. Okay, but in case of Syria, this is the XRD pattern of cerium oxide and this is of YS set. You see that we get a similar pattern to cerium oxide and YS set. Similar, of course, they are shifted. You won't be able to make out the shift. I wish I had shown you the zoomed version, but you gotta trust me on that. Okay, but it is single phasic, right? So that means YS set and Syria have formed the solid solution. If you ask me something beyond this, why did this happen and why did this not happen, even though they have same structure, all of them, the size difference between thorium 4 plus and yttrium zirconium is much larger than cerium and yttrium. So cerium and yttrium zirconium they tend to form friends easily. They like forming solid solution. This doesn't happen in case of thoria. Hume 3 rules, similarity in ionic sizes, everything else being equal. Okay. So this is a Vegard's law. Once I saw that I have got a solid solution formation and I'm showing you only 50-50, but I did it at every composition. And this particular system also showed Vegard's law. Okay, that means it indeed was dependent on their relative ionic radii. Cerium is bigger than the combination of yttrium and zirconium. So as I am putting more and more cerium, the lattice parameter is increasing and it almost falls on a straight line. Okay, so this is an example of how you can use density measurement. I put calcium oxide in zirconia, and whatever you see these dotted line, they are okay. Uh, Theoretically, I thought to myself, anybody, not but the experimental, that if the cations were going, if it was forming a, because Ca2 plus is smaller than Zr4 plus, it will form anion vacant or cation excess. If it was cation excess, then the density should fall on this line. If it was anion vacancies, it should decrease much sharply and it will fall on this line. So the compositions are made and the experimental density are measured by Archimedes principle, and these are those dotted lines. So depending on the matching of experimental data with the data that you calculate, assuming one mechanism and the other mechanism, we can find out what is the mechanism of solid solution formation by density measurement. Similarly, this is CaF2 in YF3. Whether it will form interstitial anion or cation vacant solid solution can be determined by matching up of theoretical and experimental data. So we will finish our lecture today. We talked about non-stoichiometry. Why are they non-stoichiometry? Because they are creating either cation vacant or anion. Basically, it is creating vacancy or excess on one of the lattice side. So it is disturbing the stoichiometry of your material. How? NaCa vacancy Cl. Vacancy is nothing but a empty spot. So I can remove this. Na1 minus x CaX. Okay. So it has actually, now suppose there were 100 is to 100 cation, because I have one a vacancy here, they have become 99 is to 100. So they have affected the stoichiometry. So they are non-stoichiometric defect. We studied about the types of solid solutions: simple, complex, in simple, substitutional, interstitial. Aliovalent solid solution are nothing when your host and guest cation are not isovalent. When they do not have similar symmetry, you get similar charge. You do not get simple solution, rather you have to resort to some kind of vacancy and excess mechanism. We also studied about the techniques on how to study the solid solution. With this, I would want to wind up here. I'll be here for next 2 to 3 minutes. Any doubt, you can put it up in the chat box or mail me, call me, whatever is convenient to you. Okay? All right. In that case, we'll wind up the lecture. So good day to all of you, and we'll now meet on Monday with our next topic. Yeah. Thank you.